is the important bit.
Up here in the high Arctic in Norway, there's a very soft twilight as the sun's just about appearing over the snow-capped mountains. And you can see the low-down trees, typical small trees and bushes of the high Arctic. And I'm just walking along in the snow past the most extraordinary radar dishes. There's one huge one that's kind of long and square and looks almost the size of a football pitch. Another one, a classic satellite dish, just like the James Bond images pointing up into the sky. And I'm here to see an experiment called iScatter. I'm going to meet Ian McRae from the Rutherford Appleton Lab in Oxfordshire. And he's going to tell me about the experiments he's doing with these dishes pointed up into the sky to understand what's happening in the very uppermost parts of our air. Hello, Ian.
Hello, Gabriel.
Nice to meet you.
Yes, lovely day.
It's cold out here.
It is cold, but it's clear, and that's good news for later on, maybe. Of course, it's twilight at the moment. It must be nearly midday. The sun doesn't rise at this time of year. By about 2 o'clock, it'll be dark. And who knows, later on we may see some aurora.
God, I hope so. What does iScat stand for?
iScat is the European Incoherent Scatter Association. Incoherent scatter is the technique that we use. And European now is a bit of a historical curiosity. I mean, when iScat started, it started as a consortium of European countries, but now we have the Japanese, we have the Chinese as members of iScat, we have Russia buying time. And so iScat is really international, but of course, we are located in Europe, so that's why the E stays in the name.
I like the idea of incoherent scatter. I'm feeling a bit more incoherent by the minute as this temperature's dropping all around us. So tell me about, I've just been walking past these spectacular dishes. The one that's just opposite us at the moment, it doesn't really look like a classic radar dish, does it?
It doesn't, no. What you see here is a big football field-sized cylindrical antenna. So it's 120 metres by 40 metres, the size of a football pitch. And this is our VHF radar.
So what you're doing with this dish is you're generating a lot of energy and you're bouncing that up into the sky.
We're sending it up into the sky and bouncing it from the free electrons in the ionosphere, the charged region of the Earth's atmosphere that starts at about 80 kilometres above our heads. It's really where the atmosphere turns into space, as most people would think of it. It's really the outermost region of the Earth's air.
So this is probing the thinnest air that we've got?
Absolutely. And the behaviour of the electrons at that altitude is actually controlled by waves in the atmosphere that occur all the time. And there are a whole spectrum of these waves, and that explains why we can use different kinds of radars at different frequencies to bounce off those waves, and we'll always get a signal because the waves occur at such a large spectrum of wavelengths.
I like the idea that there are waves up there, because I think about the air almost as being an ocean of air, and oceans have got waves in them, haven't they?
Yeah, yes, that's right.
There's another dish behind us now, and that's the one, I sort of see that as a bit like a classic James Bond kind of radar dish. It's circular and it's pointing right up into the sky. So what's this one?
So this is the UHF antenna, and it does indeed look much more like a conventional radar that most of your listeners would expect. So this is a large parabolic dish. It's 32 metres wide, and you can see more or less it's pointed straight up at the moment, and that means it's looking up the direction of the magnetic field line, as seen from here in Tromsø. So because we're at such high latitudes, close to the pole, the magnetic field coming down to the ground is almost vertical. And so that's why the radar appears to be looking pretty much straight up.
So the magnetic field, the Earth's magnetic field is sort of going through us and down through our feet?
Yes, that's right, yes. And of course that's why we get the aurora at these latitudes, because those particles that are coming in from the Earth's magnetic environment are guided by the field. As the field lines come down almost vertically to low altitudes, those energetic particles stream down the field lines until they interact with the Earth's atmosphere.
So these are very high energy charged particles out in space?
That's right. The sun is continuously emitting a stream of energetic charged particles.
And that's the solar wind?
That's the solar wind. It can be quite highly structured. It comes from specific features on the sun. There are fast streams, there are slow streams, there are interaction regions. That stream rushes away from the sun and eventually interacts with the magnetic environment of the Earth. So it hits the Earth's magnetic field. Either those particles can be blocked and flow around the Earth, so the Earth's magnetic field is basically like an obstacle in the stream, or they can link up with the Earth's magnetic field and come directly into the Earth's magnetic environment. And what you see up at these latitudes is quite a complex interplay of directly driven processes coming directly from the solar wind and kind of storage release processes where energy has been stored up in the magnetosphere, the part of space surrounding the Earth which is dominated by the Earth's magnetic field, and then suddenly released. So the most impressive aurora you see are particles that have been accumulated in the magnetosphere and then suddenly fired back towards the Earth as the magnetosphere has been fully loaded up and reconfigures.
So this is almost like a sort of a snap, like
Yes.
elastic band or something.
It's exactly like that. The magnetosphere can basically only take so much loading, and once it's been loaded to a certain level, it snaps back, accelerates particles towards the Earth, and that is what creates the most spectacular auroral displays.
You've got this snapping, you've got this incredibly dramatic auroral displays. What would happen if the air wasn't in the way? How dangerous are they?
Certainly, at several points during the space age, there have been solar flares that would have been dangerous to astronauts if they had been in the wrong place in space.
Because of the radiation?
Yes. You've got to regard, I think, the atmosphere of the Earth and its magnetic field as being two elements of what protect us. And of course, without the atmosphere, we would effectively all be in space. So the fact that you're seeing these energetic particles interacting with the Earth's air, that's what causes the aurora.
Those parts of the atmosphere, the very uppermost parts of the atmosphere, are very far away. How do you know that that's what's happening up there?
Of course, some of these things are chemical processes. You can simulate them in the laboratory, and we can also use the ionosphere as its own natural laboratory. And that's what the heating facility down at this end of the site is all about. We're actually using the facilities of IceCap to do active experiments in space where we can control the conditions and try and create some of these processes naturally. We can even create artificial aurora, although they're very weak compared to the aurora that you would observe on a normal night here in Toronto.
You can make auroras artificially?
Oh yes, yes, but they are subvisual aurora rather than the spectacular red, green, blue aurora that you can see here.
Okay, can we go down and have a look?
Of course.
We've walked down the road now in a very frosty, ice-covered road, and we can now see this, it's like a field of antenna. It seems to be stretching as far as I can see.
Yes, you're now walking into the arrays of the heating facility, and there are actually 3 antenna arrays here. 2 of them are transmitting arrays for actually shortwave frequencies, for those of you listening on the World Service. So this is frequencies of between 3 and 8 megahertz. And then there is one receiver array, which allows us to also use the heater facility as a radar.
This doesn't look anything like the sort of dishes we were seeing. There's
No,
individual
absolutely
pillars, and they're strung together with wire. It almost looks like a very extended
Yes.
laundry facility.
So, I
Like
mean,
you're
this
washing.
would be much more like a radio transmission facility, for instance. And in fact, that's what we're doing here. We're broadcasting very high-powered, short-wave pulses up into the ionosphere. Power is sufficiently great to actually modify the properties of the ionosphere, so we can understand how the natural processes up in the ionosphere really work.
When you say heat it, you really mean sort of increase its temperature?
Well, of course, temperature doesn't mean much at those altitudes because there's not enough thickness of air for you to actually feel anything. But yes, if you treat temperature in its strict scientific sense, its thermodynamic sense, what we're doing is increasing the thermal velocity of all the particles up in the atmosphere. So to that extent, we're increasing their temperature.
You're making them more energetic?
Yes, we're making them more energetic, exactly.
I love this impression that the ionosphere is actually, it's almost a response. So the sun's particles come in and the atmosphere gets ionised, it responds in this way. It's almost like a kind of immune response.
In this case, what's creating the ionosphere is mostly extreme ultraviolet radiation from the sun. And of course, as you can see, we're not getting much solar radiation today, so that's why there isn't much ionosphere. But yes, you're right. I mean, the ionosphere is a reaction to what the sun is doing.
Almost like an immune reaction.
If you like.
I know that this is the heating building just over here to control the heating experiment. May I suggest that we go in for some hot chocolate?
Sounds a good idea, yes.
And inside the heater building, I found physicist Michael Rietveld sitting at an intriguing bank of instruments.
Okay, we're running an experiment for some German collaborators from the DLR, which is the German Space Agency. And we're basically turning the heater on and off, 10 seconds on off up to a few minutes on off. And the purpose of this experiment is to see what effect the temperature change or maybe density change in the ionosphere would have on GPS signals.
So this is satellite signals, so we know where we are, we can pinpoint our position on Earth.
That's right, it's exactly the same signals that are used for positioning.
So what exactly, you've got some computer screens here and you've got big banks of equipment around, and I'm happy to say that it's quite a lot warmer here in the control room than it is outside where I've just been. How much energy are you putting up there?
About a megawatt in total, which is quite a lot. We're radiating about a megawatt.
And what sort of area are you illuminating with that?
It's about 200 kilometers above us, and it's about 60 kilometers in diameter.
I understand about sort of looking at the atmosphere and seeing what happens, and also about going into a lab and doing experiments, but this is almost like doing an experiment on the atmosphere.
Yes, that's true. Here we have a very controlled way of doing it. We can, switch on the heat source very accurately and switch it off, and so we can control a lot of things that we can't do by looking at the natural ionosphere.
Suitably fortified with hot chocolate, we're now just going to go outside for one last look. There's just the last shreds of twilight, and you can tell that the temperature's really noticeably colder now, but you can still have just enough light for us to climb up onto the dish. We've been waiting for the experiment to be over. It's now finished. We can't go up on the antenna when the experiment's happening, or we would be fried. But now we're going to go and get really up close and personal with what's really happening when these experiments go ahead. Oh, so the dish is pointing sideways now. It was pointing directly up before, but now I can see it pointing almost into the mountain.
Yes, that's right, and that's because of us, because we are about to go climbing.
We climbed, and we climbed, and the steps and the ladders got steeper and steeper.
We're up on is this the topmost stage now?
This is as far as we can go, yes.
That ladder is a bit scary.
I'm glad you enjoyed it.
So, beautiful view of the mountains from up here though.
Yes, wonderful. The store here will actually take us into the hub room, which is the room behind the prime focus where the first stage of the receiver for iSCAT is.
Can we go in?
I think so. A small and cramped room of electronics. So this is where the signal actually comes in to be beamed out from the dish into the ionosphere.
How much energy is going up there and how much coming back?
We're transmitting of order 1 megawatt out into the ionosphere.
That's quite a lot.
Yeah, maybe, and we're getting back a millionth of what we transmit, basically.
Wow. So most of that's really just disappearing
So
out into
most of
space.
the energy we're transmitting from this radar is disappearing straight out into space. And that's why we need a big dish like this to collect the tiny fraction of the energy that we get, and why we need very sensitive receivers and cooled detectors and so forth to really sense it above the noise.
Well, tell me about the energy that's out there in space, because you talked about some of the particles, the solar wind. Just how energetic are those particles that are heading for the Earth?
The particles vary greatly in energy, so we go from particles which are energetic enough to burrow deep inside spacecraft and really damage spacecraft electronics and so on, to much softer particles, the particles that cause the aurora, particularly the red and green aurora that you see a lot from here.
Now, sometimes the sun will put out something really big, something called a coronal mass ejection. That's what a giant blob of glowing plasma.
Right.
Can you tell me about what happens when that takes place?
Basically, what happens is that a big cloud of energetic solar wind is then heading towards the Earth.
And what do you see when something like that happens?
Well, in that case, you might see, for instance, very spectacular aurora. You might see strong solar storms. So you might see the aurora pushed even very far south of here. The biggest solar event that we've ever recorded was something called the Carrington flare. It happened in 1859. It's a very famous event in solar terrestrial physics. And on that occasion, aurora was seen as far south as Hawaii.